Hello everyone, my name is Bhiman. I am a PhD student in computer science at the University of Pittsburgh, and this is the second part of our three-part series in understanding DeepSeek-R1. Therefore, I would highly recommend anyone who haven't watched the part 1 to watch it. The link is in the description. So far, we have discussed the pre-training of these models and found out that DeepSeek R10, though has architectural differences, those differences are aimed more towards efficiency than reasoning. However, there's an important aspect of pre-training I haven't discussed yet. Can you guess? It's data. Interestingly, Llama 3's pre-training data contains only about 13% of coding and math content, whereas DeepSeek R10 contains a lot more. While the exact percentage isn't disclosed, the authors mention that they have doubled down on coding and math data in every generation of these models. Since reasoning performance is evaluated largely through coding and maths tasks, this design choice likely plays a significant role in DeepSeek's performance, even if no one's pinned down exactly how much. After pre-training, DeepSeek R10 skips the SFT stage and moves directly to the RL stage. Unlike others, it uses a new RL algorithm, GRPO. So let's understand how GRPO works and why do the authors need this new algorithm. But before that, first we need to understand how the conventional RLHF algorithm PPO works. In reinforcement learning, there are two main entities, the actor and the environment. The actor performs the action, whereas the environment provides feedback in form of rewards. Let me explain this with an analogy from my sweet childhood memories. This is me, the actor, taking exam at school. I scored decently. These are my parents, the environment, who reward me with scolding because I didn't score high enough. In technical terms, I represent the policy model and my parents represent the reward model. Afraid of further scolding, I studied hard and scored a 90. But do you know what? I still got scolding as a reward. Why? Because my score was still lower than the topper, the ideal student my parents compare me to. This topper represents the reference model. So, the final reward is combination of two things. My parents' direct reaction, which is the reward model, and their disappointment from how far I am from the topper, which is the reference model. This combination forms the final reward. But we are not done yet. Each time I take an exam, my parents already have a certain expectation of how I will do before they even see the results. This expectation comes from the value model. The difference between the actual reward and the expected value is what determines how much scolding I get. This difference is known as the advantage. However, my parents aren't as harsh as they sound. They want me to improve gradually. So they keep a track of how I had been performing, that is past advantages, and smooth out their feedback over time. This tracker is known as Generalized Advantage Estimation, or GAE for short. GAE also ensures their expectations don't swing too widely. It stabilizes both feedback and the expectation. As you can see, there are 4 models involved, but only 2 of them are trained. Those which receive the feedback, the policy model and the value model. And that, my friends, is the PPO algorithm. I hope the overall working of PPO is clear. Let's switch to the technical diagram. In the case of training a large language model, the policy model is the language model itself. Initially, it is just a copy of the reference model which was obtained from the earlier supervised fine-tuning step. You might wonder, why are we copying the same model? The reason is the reference model is not trained any further because it's already quite good. However, we want to make it better by reducing the undesired behaviors. So we take copy of it and train this copy, now called the policy model, to retain all good things it has learned while also avoiding harmful, non-factual, or undesirable outputs. This policy model is the one that's eventually released to the public, the model that powers the application we interact with every day, like ChatGPT and Gemini. Now, here's the interesting part. DeepSeek R10, instead of using PPO, uses GRPO, that is Group Relative Policy Optimization. You might ask, if other popular LLMs are using PPO, why might the DeepSeek team switch to GRPO? The major difference you will notice from the diagram is that GRPO doesn't require a value model. What's the advantage of removing this value model? Do you remember what the value model does? It provides the expected output. And if you think about it, to predict the expected output of a language model, you essentially need another language model. In PPO, this value model is like a third copy that is also trained alongside the policy model. So, in PPO, we have to maintain three large models, two of which are trained simultaneously. The reward model can sometimes be small and separate, but the policy, reference, and value models all need to be similar in size. Can you guess how much GPU memory these models require for training? Let me give you a rough idea. Let's calculate the GPU memory needed for the policy model of DeepSeek R10. If you watched my first video, you know that DeepSeek R10 has 671 billion parameters. If you haven't, this is the sign to check it out. The link is in the description. The rule of thumb is, for every 1 billion parameters, loading a model in floating point 16 precision requires 2 GB of GPU memory. So for 671 billion parameters is 671 times 2 equals 1342 GB of GPU memory. But this is just to load the model. How about training? Twice that? Wrong.
Another one.
4 times? Wrong.
Another one.
6 times? Wrong.
Another one.
8 times? Yes. Without optimizations, the training requires around 8 times the memory, and even with optimizations, it's at least 6 times. The main takeaway is training a 671 billion parameter model would need at least 1342 times 6, that is 8052 GB of GPU memory. Fun fact, the NVIDIA H100 GPU, the industry standard for AI inference and training, has only 80 GB of GPU memory. So, to train just one policy model, you need hundreds of these GPUs. And do you know the cost of one H100? Around $30,000 each. So, for 100 GPUs, you need $3 million. But wait, we need another 100 GPUs for the value model and another 50 GPUs to handle the reference and reward model. Add all that up, and training DeepSeek R10 with PPO would require around 7.5 million US dollars just for the GPUs. No wonder Nvidia's stock is skyrocketing. Disclaimer, I'm not a financial advisor and this is not a financial advice. And that's just the GPU cost. I haven't even included storage, electricity, engineers, and their food so that they can make a day in a life TikTok. So, what's the key takeaway of all these calculations beside me realizing how broke I am? Training LLMs with PPO is extremely expensive because we have to train two large models simultaneously. GRPO cuts this cost by half since it removes the value model and trains only a single policy model. Does this mean we don't need the expected value anymore? No, we still need it. It's essential. But GRPO computes it in a clever way. Instead of training a separate value model, it samples multiple outputs and takes their average, which serves as the expected value. And that, my friends, is the GRPO algorithm used by DeepSeek R10, which gets rid of the value model, significantly reducing the cost. You might be thinking, wait, this is all about efficiency. How did DeepSeek R10 develop its reasoning ability which made it so popular? That's a good question, because I said this capability emerged in the RL step. The answer lies in two things. First, is the query given to DeepSeek-R1 0 is the same what's given to a conventional large language model? Hint, the answer is hidden in what I mentioned at the start of this video. Second, is the reward model used by DeepSeek-R1 0 the same as the one used by conventional LLMs? While you think, here's a third question. If DeepSeek-R1 0 already gained the reasoning ability, why did the team release DeepSeek-R1? I will answer all of these in the third and final video of this Understanding DeepSeek-R1 series. So stay tuned and I will see you in the next one.